Guys, hi, welcome back. Now we are moving into the sensors and transducers. The first sensor that we are looking into is the capacitive transducer. Okay, um, we all know capacitor. Basically, it is very much used to charge, to store, and charges. All right, but basically, we can use the capacitor, in the different construction concept to become a sensor, basically. All right. So they say here this type of transducer will change the physical quantity into the change in capacitance. All right. So when they detect any change in the physical quantity, they will produce variation or change in the um, capacitance. All right. So a very simple capacitive transducer is a two parallel plates separated by dielectric or insulating material. All right. So we all know the shape and the type of capacitor. Basically is like a solid state device with no moving parts. Okay. When we want to make the capacitor into a sensor, we have to construct it differently, where we have to allow some parts to be in motion, so that we can detect movement and motion that induce the moving parts of the capacitor. Okay, just look at this diagram. You have two plates, top and down, top and bottom. Okay, you have labeled as a moving plate. One is the fixed plate, so you have two plate of the capacitor. And then right in the middle, you have some kind of dielectric material, and you have X over there, which basically define the distance between um, the top and bottom plate, the moving plate and the fixed plate. All right. So as I mentioned in the previous slides, basically this capacitor sense in the change in mechanical. In this case, the moving plates, the X, okay, and convert those physical change into the change in capacitance C. So you can basically observe the whole stories from the formula. You have C of X over there. You have equal to epsilon A over X. All right. So A is basically the area of the plate, and X is the distance, and epsilon is basically the dielectric constant or permittivity, basically. All right. So the epsilon is here in this case is epsilon r and epsilon naught, which you can always replace in the formula. Okay. So from here, from this formula, you can see C. The value of C is depending on the epsilon. It's depending on the A area. It's depending on X, the separation between two plates. All right. So in this case, if you change any of these parameters, you are affecting the values of C, meaning that to make the capacitor as a sensor, you can induce change in any of these three values. If you change if you move, or if you change the dielectric material, the C will change. If you move the area, the overlapping area of top and bottom plate, which is the A, you are observing a different C capacitance. And if you change the value of X, which is the distance between top and bottom plate, you are changing the value of C. So you have three options if you want to change a simple capacitor to a sensor. Okay. The basic operation here, as I mentioned before, there are three ways to change the capacitance. Variation of the distance, D, or in the diagram just now is X, labeled as X. The variation of area shared by both two plates, overlapping area by effective overlapping area for the top and bottom plates, the A, and the variation of the dielectric constant, the epsilon. So if you change the material in between, basically you are changing the capacitance. All right. So figure 5.3. Okay. This is with the effect of D. The diagram on your left. You move the horizontally one of the plate. You are affecting the D, the distance between two plates, and from there you have variation in C. And on the right, the diagram on your right is basically you are changing the A. Originally, the parallel plate overlapping, they have the whole area of A overlap. When you slide this thing up and down, basically you are reducing the number, the area of overlapping area over there. The A is getting smaller. So when A is smaller, your C will be smaller. Okay. So here you have many things, but they are all describing the same things. All right. You change the electric. The first diagram, the top first left, you are changing the dielectric material. The second one, you are changing the D. The third one, basically, you are changing the A. All right. And the last one over there, you know, you have epsilon 1, epsilon 2. Basically, you are sliding the dielectric material in between the plates. So you are changing because for the capacitor to happen, you have to be concerned on the area overlap area from the top plane to the top plate to the bottom plate. So you have to consider everything in between. For example, here you have originally you have epsilon 2 as a material. Now you are sliding E2 and you are allowing a gap or a space, which is the epsilon 1. So epsilon 2 maybe it's a different material. Epsilon 1 maybe it's just an air gap. So if this thing happen, you have to consider the epsilon 1 and epsilon 2 into the consideration, in which this thing will change the value of capacitance. All right. Same thing in the case of you change the separation distance between two plates. This is the formula how to get the C. Epsilon is still there, epsilon not epsilon R is there, and now D, or the distance now is changing to D plus X because you are changing the distance. All right. The second one is when you change the plate. Look at the small diagram there. Basically, you still have the original formulation epsilon A over D. Now the effective overlap area is changing, so you have to do something with the overlap. You have to recalculate the area of overlapping between these two plates. All right. So the last way of changing the they call that capacitance is to change the dielectric material in between these two plates, the top plate and the bottom plate. In this case, you have two different materials, as I mentioned just now, epsilon 1 and epsilon 2. But then be concerned with for everything, you know, that stay in between these two plates. All right. So this is the formula you have to calculate using the first material, and you have to plus capacitance using the second material. And of course, you have to basically know the size of the overlapping material, okay, so that everything stay between these two plates. Right. This is example. You can always go through and solve it. Basically, this is for the cylinder displacement. You know, the formula is short and simple. C is equal to epsilon not epsilon r multiplied by the area divided by the distance. So capacitor can take many shapes. Not necessarily has to be square. Two plates can take you know, the shape of a cylinder, in which you still have the area, you still have the overlapping. Sorry, you still have the distance between two material, and in between those materials, you still have the you still have dielectric material represented by epsilon, basically. So as long as you understand this this formula that with three parameters that change the C, you know, for whatever shape or design that you are looking at, the principle is still the same. Okay. Okay, let me see. Yeah, there are examples here which is in which you can basically see. All right, the same thing here. All you have to be concerned is what is the area, effective area of overlapping. If you have a square plate, is like the width times the height, for example, okay, or the width times the length. And then in this case, you have a cylinder, so the overlapping space, you have to use whatever formula to make sure that all the overlapping space is very much covered, you know. And then you have to take care of things here that may represent the overlapping area A, the epsilon, and the distance between this plate. So you have radius over here, you have heights, you have the whole length of things. You can basically take all these parameters correctly and just put it in the same formula that we have been seeing. Okay, you can see that they still go back to the same formula of capacitance, just you have to get the right, for example, A here you have to use the different formula. If we were talking about a simple plate, the A is just, as I mentioned, is the length times the width. Okay, but this is a cylinder, you have to use A is equal to 2 pi RL. So you have to extract the information properly from the design and just put everything, replace everything into the simple formula. Okay. So for the capacitive transducer, basically we are using Wheatstone bridge. Okay, you can always refer back to the lecture in the Wheatstone bridge. Wheatstone bridge is not only good for transducer with variation of R or resistance, it is also good for transducer with variation of capacitance C. Okay. Same arrangement, same construction, just replace the R with C. So basically you are getting more or less the same Wheatstone bridge. Okay, so that's all for lecture 8 on the capacitive transducer. I'll see you again in the next lecture. Goodbye.